So let's look at vectors, and I'll work through a couple problems that are like you'll see on the test. But yeah, as always, you can look at the old tests and look at those. But I'll work through ones that are similar, and then we might look at some old tests too. Because vectors come up in two different places. We see it with forces and with fields. Okay, so let's look at the forces. First of all, the magnitude of the force is this K Q1 Q2 over R squared. That's on your equation sheet. And the magnitude of the electric field is K Q over R squared. Right, so those are both on the equation sheet, and those are just the magnitudes of those forces. So let's say that I have two charged particles like this. Let's say that they're on a triangle like this, and I want to know what is the, let's say that this one is plus 3 nanocoulombs we'll say that this is 5 minus 5. You know, to make the numbers real easy, I'm going to just make this minus 5 coulombs. All right, that's not very realistic, but just to make the numbers easy, we'll just make it minus 5 coulombs. And let's say I want to know what is the magnitude and the direction of the force on this particle. Now the first thing you want to do is, oh, and then I also need some angles here or some sides. Let's say that this is 2 meters and 2 meters. It's an equilateral right triangle. So the first thing you want to do is just draw your vector. And so these are positive and negative charges, so they're going to attract or repel. That's a question. It's sort of a question. They'll attract, right? Opposite charges will attract, like charges will repel. So, yes? Okay, so on that charge, I will have a force that's in that direction. And so I need to know a couple things about that. I need to know what is the direction and what is the magnitude. The direction will be just what is this angle right here. Okay? And so in order to find that, and then to find the magnitude, I would say what is the magnitude? I can calculate it here. Let's find the magnitude first. So that's going to be 9 times 10 to the 9th times Q1 times Q2 over R squared. So that's going to be 3 times 10 to the minus 9 times 5 coulombs divided by the distance, which is going to be this distance right here. Okay, 2.8 meters. We get that by saying the square root of 2 squared plus 2 squared. K is Coulomb's constant. That's going to be on your equation. It's on there, but it's good just to know because we're going to use it. Right. I try to always make the numbers pretty easy to work out. So notice here, these cancel out, and I'm left with 9 times 3 times 5 over 2.8. And that gives me a force of 27.5 over 2.8, 48 newtons is what I get. So that's the magnitude. And then to find the direction, we just have to do a little bit of geometry and right angle trigonometry. I want to know this angle. I know that this angle is 90 degrees. Draw that on there. I want to know what theta is. Did you not get that? 27 times 5 divided by 2.8. Oh yeah, it is supposed to be squared. You're right. I don't think I did that. That's 17.2. Thank you. I'm sorry. This should be squared, and this works out to be 17.2 newtons. Okay, so back to the direction. I need to know this angle theta right here. But I also know, let me redraw this a little bit. So I'm going to draw that triangle, that equilateral right triangle. And then I'll draw my coordinate system. And I'm looking for this angle theta. So if I can find this angle, theta would just be 90 minus that angle. Look, I know what this angle is because this is 2 meters, 2 meters. So what is this angle right here? Equilateral right triangle has which angles? They're all equal, right? So I have a 90 degree and 45 degrees, yes. So that's 45 degrees. They all have 180. 45, 90, that's like 180. So that tells me then that theta is 45 degrees. So theta here is equal to 90 minus 45, and that's equal to 45 degrees. So the answer would be 17.2 newtons at 45 degrees below the plus x-axis. Well, it is simpler, but we use some of the same steps that we used in those questions that we did in class and in your homework, but there are just fewer of the steps. This one's a lot simpler because there are only 2 particles instead of 3. But let's do another one that'll be a little more complicated where we have 2 particles, but we're looking at the electric field, and then that'll be slightly more complicated than this one.
So what would the question be, like written down?
It would give you this figure, and it would say, give the magnitude and direction of the force on the 3 nanocoulomb charge.
Okay, so the magnitude and the direction.
Right, this is the magnitude, this is the direction. So those are probably 2 separate questions.
Okay, so the magnitude, you use that force equation?
Right, to find the magnitude, if you're looking for the force, you use this. If you're looking for the electric field, you use this.
Okay.
Let's do another one for electric field. The vector addition works a lot similarly, but it can be a little more complicated because you have, well, let me just show you. So let's give you a configuration of charges. Can I go down from here? Let me think. Let's say that I have 2 charges right here. This one will be plus 3 nanocoulombs. This one will be minus 2 nanocoulombs. Actually, no, I'm sorry. Let's make this one 5 nanocoulombs. Make the numbers work out easily. And we will put this on, I want to know the electric field at this point. This point is a distance 4 meters from that minus 2 nanocoulomb charge, and these 2 charges are a distance of 5 meters. All right, so that should stand out to you. Oh no, not 5 meters, I'm sorry, 3 meters. That should stand out to you now with a 3 and a 4 as a 3, 4, 5 triangle. And you'll probably see a 3, 4, 5. Well, shoot. I don't know if you will see a 3, 4, 5 on this test, but you can see that. All right, so I want to know the electric field at this point. That would be the question. What is the electric field at that point? And since the electric field is a vector quantity, I need to know both the magnitude and the direction. Okay? So this was a little more complicated because now I'm going to have 2 vectors acting at that point. Let's draw our vectors at that point. And this is where you want to use that positive test charge. So you ask yourself, if I have a positive test charge at that point, what is the direction of the force on that positive test charge? So take, for example, the minus 2 nanocoulomb charge. The direction of the force on a positive test charge would be to the left or right. It would be to the left because a positive and a negative charge are going to be repulsive, or going to be attractive rather. So the direction of the electric field here will be in that direction. I'll call that E1. And then the direction of the electric field due to this charge will be in this direction, and I'll call that E2. So now we can do a couple things. Let's first find the magnitudes of E1 and E2. And so E1 will be K, which is 9 times 10 to the 9th, Q, which is 2 times 10 to the minus 9, divided by 4 squared. KQ over R squared. So that is, this cancels. I get 18 over 16, which I get 1.125. I'll just call it 1.1. Okay, that's E1. And then E2 is 9 times 10 to the 9th. Q is this charge, 5 times 10 to the minus 9, divided by this distance right here. And recognize my right triangle. It's a 3, 4, 5 triangle. But if you don't remember that, or if there's some funky numbers, you say the square root of 3 squared plus 4 squared. That's equal to 5 from the Pythagorean theorem. Okay, so that's divided by 5 squared. I can cancel some things here, and I get 9/5, which is what? I think 1.8 newtons. So those are the magnitudes of my vectors. I have E1 is 1.1 newtons, and E2 is 1.8 newtons.
So then it also looks a lot weird at this point because you find that and then you find the direction as well.
Right. Okay. Honestly, I could probably make this a little simpler, and we can look at some old test questions. But you really need to know how to do these steps. You're probably not going to see them all in one problem, but you can see them spread around other problems.
So it would be like find the magnitude and then you that's the direction.
Let me just show you. After we do this one, we'll look at some old test questions, okay? So now my next task is to find out what is this angle. And we need to recognize that this angle is equal to this angle. Because if you notice, let me see, you have a highlighter here? I think I do. No, I'll just use yellow. I have two lines here that cross. Anytime I have two lines that cross, those two angles are equal. I think they're called, I don't know.
Just alternating.
Alternate. That's who said that. Maybe this guy. Yeah. Somebody smarter than me. So that's an alternating angle. All right. Or alternate angle or whatever. So I need to know what this angle is right here. But look, it's a 3, 4, 5 triangle. So I know that's 37 degrees. But if you don't know that right off, you would just say theta is the inverse tan of opposite over adjacent. That's 3 over 4. That's SOHCAHTOA. And that's equal to 37 degrees. Should be.
Can you go over that real fast? I think
Sure.
that's
Absolutely. So remember your mnemonic? SOHCAHTOA. This tells what sine, cosine, and tangent are. So if I have a triangle with an angle theta right here, this is the adjacent side to that angle, this is the opposite side to that angle, and this is the hypotenuse to that angle, to that triangle. And so the sine of theta is opposite over hypotenuse. So the cosine is adjacent over hypotenuse, and then one that we use more commonly is the tangent of the theta is opposite over adjacent. And so here where we are finding this angle right here, the opposite side to that angle is, to the 37 degree angle, is the 3, and the adjacent side is the 4. That's why I use 3 over 4. And further, if you want to find the angle, if you want to find theta, you say theta is the inverse tan of opposite over adjacent. It's been a while, even in, like, we didn't use that very much in the last half of 101, so it's good to review those things. Okay? Unfortunately, after this chapter, I'm not going to see it again, so it's good news for y'all. And you probably use it elsewhere. Yeah, you put using calculus a lot, right? Your trig functions and stuff. Okay. All right. What's important? So let me erase this stuff, this trig review right here. Simple space. So now I know this angle is 37 degrees. Okay? Now I want to find the x and y components of this force. I'll do them in purple. The y component will be 1.8 sine of 37. The x component will be 1.8 cosine 37. That comes about from our definition of sine and cosine. If I think about my triangle, if this is my angle, theta, cosine of theta is the y component over the x component. Excuse me, I'm sorry, no, that's not right. Is the x component over the hypotenuse. And so the x component is the hypotenuse, which is this vector right here. It's the hypotenuse of my right triangle. The x component is the hypotenuse times cosine theta. So that's where this comes from, this 1.8 cosine 37. Is this okay for y'all? Sort of, kind of? Okay, we're going to do some other practice problems after this one. I'm trying to set that in a little bit. Okay, so now I can redraw my vectors. I have 1.1 in this direction, 1.8 cosine 37. I get 1.4. Is that right? Yeah. And then 1.8 sine of 37. I get 1.1 for that. Okay? Now, anytime I have more than one vector on one axis, I add them up. So, or I do the vector sum. So I have 1.1 and 0.3 on this axis. That's just 1.4 minus 1.1. Adding up those x components. Now realizing that, hey, this is just another right triangle. I have 0.3, 1.1. I want to know the length of this vector and the angle, I'll call it theta again. To find the length of that vector, I say the square root of 1.1 squared plus 0.3 squared. That is what it is. I get 1.14. All right, this is Newton per Coulomb, actually. And then to find the angle, theta, I'm going to use that inverse tan, the same way I did before, of 1.1 over 0.3. $75 degrees? Does that make sense? That sort of makes sense, yeah, because the opposite side is a lot bigger than the adjacent side, so this angle should be bigger than 45, because this is bigger than this. Is that right? Let's do another question. Like, we'll look at an old test. Is that okay if we do one or two more? How are y'all feeling on this?
Okay, it's just like, is it above the x-axis?
It is above the x-axis, yeah. So you will see that qualifier. It's the vector above or below the x-axis. Here's above.
Okay, I think I answered all the questions. But what did we do at first when I see we found the hypotenuse? That's what the 1.14
Yeah.
is. I was like, well, why didn't we use that to find out?
Let's look at an old test, Josh, because this has a lot of steps still in it. And
Usually the old tests, they don't really have those detailed, like, it's just like one, it's like a linear problem, not like another.
yeah, I understand what you're saying. Let's see.
When you did 1.8 sine 37 degrees and 1.8 cosine 37 degrees, is that something from the previous class?
Sort of. It goes back to our cosine and sine definitions. Your x component, as far as we're concerned, and it'll always be this way for this class, as far as we're concerned, the x component will always be the vector times the cosine. The y component will always be the vector times the sine. All right. Let's take a look at an old test. We'll see it again. Okay, with this one, right here, number 8, we're not going to worry about the magnitude right now, so let's look at the direction. This one's actually fairly straightforward. So what is the direction of the force on the 5 nanocoulomb? So first of all, you want to ask yourself, well, what is the direction of the vector? Just draw the vector, and the vector is going to be in this direction. And then I draw my coordinate system. It's going to look like that. And I want to know what is this angle right here. And then once we find that angle, we'll look at the options and see sort of how it fits in. Now, notice this is a 3, 4, 5 triangle, so as we did before, we know that this angle is 37 degrees, and so this angle is 53 degrees, 90 minus 37. And so an answer would be that the force is 53 degrees below the x-axis, the positive x-axis. Now let's see what the options are. Oh yeah, so that is the answer. C is the right answer. 53 below the positive x-axis.
And it's below because of the direction.
Right. Because if I look at my coordinate system, this is x, this is y, it's below that axis. If it were above, it would be in this direction. It can be above or below the negative x-axis. I'm not going to give the angle with respect to the y-axis. That's just my standard. Okay? So it's a lot easier, but there are still some of the same steps that you need to, I mean, we didn't need to know the cosine and sine because if you know the 3, 4, 5 triangle, then you don't need to know it, but you could, if you had a different kind of triangle to find this angle, you would say that the tangent of that angle is opposite over adjacent, that's 3 over 4, and then solve that for theta, which is the inverse tan of 3 over 4, which is 37 degrees. Let me look at pull up another one.
I have one quick question.
Yeah.
How many problems are going to be on the test?
25-ish, plus or minus 1 or 2.
And what are they going to be mostly covering? Like,
I don't know if we're going to get to capacitors. So chapter 2 is split between potential and capacitance. And probably we might get a little bit into capacitors, but it'll be just sort of like I'll give you some very basic facts and basically tell you what questions to be prepared for, a couple of questions. So most of it's going to be forces, fields, there will be some basic static charge stuff, and potential.
Can I go over like possible ways if this vector was here or there so I don't like make a mistake, because I think I wouldn't have caught that 53 degrees. It's been a while since I did those geometry.
Okay. Yeah.
Like I remember, but then I forgot.
Well, it depends on the magnitude of the charge. Come back and look at this one, okay? Okay to do all forces and fields, vector stuff on this during this time? That's sort of the bulk of it, right? That is a big part of it. You'll also need to know about static charges and sort of the types of different charging, conduction, induction, that type of thing that we talked about in class. You're in the class section. Are you in the in class? Yeah. Okay. So how could you get different answers to this? Well, you could say that this was positive 10, and if that were positive 10, then your force vector would look like that, and it would be quite different. We could draw our coordinate system like here, and then it's a matter of, well, shoot, what is this angle? You got to figure out what that angle is. I always find it helpful to draw my triangle. So there's my triangle. And then realize that this vector is just an extension of that triangle. So you tell me, what is that angle theta? I mean, I know this triangle has angles 53 degrees and 37 degrees right there. But if I want to know that angle, what is it going to be? It's going to be not 37. No. That's a good guess. This angle will be 37 degrees. Because remember, look at here. I got my two lines crossing here and here. So this angle will equal this angle. And since this angle is 37, this will be 90 minus 37, or 53.
Is that the answer, or like where, what?
It would be, yeah, so if those two particles were positive, right, they're not in the problem, but if they were both positive and your force vector looked like that, the answer would be 53 degrees above the negative x-axis. Or remember, you can express it in different ways too. So I could say 53 degrees above the negative x-axis. Or if that answer is not there, it could also be 127 degrees from the positive x-axis. I can always measure my angle from the positive x-axis. That's always allowed. So if first, just look at the closest axis, and that's probably going to be the answer. But if you don't see it there, we'll say, well, how many degrees is it from the positive x-axis? Either, well, we'll always measure it. If it's in a different quadrant, we'll always measure in the counterclockwise direction. Like we always measure our angles as if you're going in this direction. Okay. Unless, we're just going right below the positive x-axis or right below the negative x-axis. Okay, is that clear? So you see, it's less complicated than the ones we did in class, but still a lot of the same pieces to fit together.
So how am I gonna know which one to pick, like 37 degrees and 53 degrees? Because like, I don't know, they're so next to each other, so I might make a mistake and put 37 and 53.
Yeah, then you would miss the problem.
Yeah, I know.
But you know what you want to do, right? Well, if you draw it carefully, you can see it. You can see that this angle is less than this angle. But you just have to recognize that these two lines are crossing so that these two angles are equal. Whereas, I can show you the angle that's 53 degrees.
Which one to choose?
Yeah, which one?
That's the same thing I thought, like, how do we know exactly? Like,
Which one to choose to describe the force?
Yeah,
It's going to be from the x-axis.
so whatever one's.
I'll never measure an angle from the y-axis.
Oh, okay.
Okay?
Okay.
I'll either measure from the negative or the positive x-axis. I mean, did I give any from the y-axis in this problem? Let's go down. Oh, I did, but it was wrong. I just threw it in.
That's the same thing I was thinking, though, like, it almost feels like, what if I actually took the wrong one? That would be.
Well, don't accident. Don't accident. Okay?
That's the old ones.
Okay. We don't use much trig or geometry, but what we use is important. All right? Can I clear this? How y'all feeling with this? What is the electric field at point A? Oh, so this one is like that electric field problem, but it's a little easier, but it still has all the pieces. I'm just going to outline what you would do. If you want me to work through it, I will. But first, I would ask, what are the vectors that act at this point? The one due to the plus 5 nanocoulomb charge will be down. I'll call that E1. The one due to the negative 10 nanocoulomb charge will be in this direction. That'll be E2. I know that I imagine my positive test charge here, and I ask myself, what is the direction of the force? The force due to this charge on my imaginary positive test charge would be down. That's how we find the direction of the electric field. We imagine a positive test charge. The force due to this charge would be to the right, because they would attract. A negative and a positive charge would attract. A positive and a positive charge would repel. So my electric field vectors look like this. Now, what I'm asking here is, what is the magnitude? And the magnitude will be the sum, the vector sum of these two vectors. So I want to know what is the length of that vector, and then that'll be the answer. And so I have to find out what is E1, KQ over R squared. What is E2? Likewise, KQ over R squared. And then to find the magnitude of E, I would say the square root of E1 squared plus E2 squared. I could also ask the direction. Work through that?
So
The answer would be
the red line that you have shown.
is the length of the red line, yeah. And the length of the red line is given by this. You would find the two magnitudes of E1 and E2. These are like the legs of my right triangle. And so I use the Pythagorean theorem to find the length of the hypotenuse. Do you want me to work through that? Because this is very much like a question you'll have.
Okay, yeah.
Okay, yeah. I have a couple of things. Is that okay to work?
This might be a dumb question, but so the Pythagorean theorem is to find the hypotenuse.
Yeah, the Pythagorean theorem describes the relationship between the two legs of the hypotenuse, that a squared plus b squared equals c squared. And
Why
so,
is that in the middle of it instead of along the side?
well, I can redraw these vectors if you like. I think I understand what you're asking, but let me redraw it and see if it makes more sense to you. I can take this vector and get rid of it, and just draw it instead over here. I can do that to vectors. That was E1.
Sorry.
Can we sorry? Okay, I can move vectors around however I want, as long as I don't change their magnitude or direction.
Agreed.
Don't be sorry. Okay. All right. You want me to work through that or no? Okay. So let's look at this. So the first thing I want to do is just find my magnitudes. So that's 9 times 10 to the 9th. Q for E1 is 5 times 10 to the minus 9 over r squared, which was 4 meters squared. So that's, this cancels here and here. 9 times 5 over 16 is 2.8. And then E2 is 9 times 10 to the 9, 10 times 10 to the minus 9, times 3, or over 3 squared. Cancels, 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 cancels. Just leaves me with 10. So my two vectors are E1 is 2.8, E2 is 10. So to find the length of the hypotenuse, I say the square root of 10 squared plus 2.8 squared square root it, I get 10.4 newtons per Coulomb. So C is the right answer. Could also ask, what is this angle right here? What is this angle theta? Theta, like in a separate question, is the inverse tan of 2.8 over 10. Because that's the opposite side over the adjacent side. The side opposite that angle theta and the side adjacent that angle theta. And that's 0.28 inverse tan. I get 15 degrees or 16 degrees. Below the plus x-axis. Or you could say 344 degrees from the plus x-axis. And that would mean that I could start at the plus x-axis and go around 344 degrees. And I would say 360 minus 16 feet, that's 344. Isn't that right? Yeah, that's right. Okay. These problems are a little easier to chew on. I mean, when you do the full 2D vector problem in class, it's like, oh, right? But it still has a lot of the same components, a lot of the same work.
The only stupid question I have is for your r squared and the distance squared, how do you choose, like how do you know you're not going to be looking for that hypotenuse?
Okay, well, in this one, we're looking particularly for the electric field at this point. And so the electric field at this point is due to this charge, which is 3 meters away.
Okay.
And this charge, which is 4 meters away. Now, if there was a charge up here, then I would use the hypotenuse. Now that would find
Yeah,
that.
because sometimes I notice that we do that, and I just don't know exactly.
This is what I do. If it touches the line, you don't do the sine
That's a good way to think about it. You don't have to do that diagram there. Oh, you're right. That's a good way to think about it. Okay?
Yeah, so it is directly related to use.
I just realized how to grow over my geometry.
Yeah, there's not a whole lot, but you know, right angle trig and right angle
I'm
trig.
always so dyslexic and it's like I'm good at every single math thing, and then you got the degrees and I'm like, oh.
I know, and you know, you're taking the exam, it's like, oh, I got 50, I got an hour to do 60,000 questions that he just gave me. I hate exams.
Why do you have to give us time?
Because when I take exams, I learn a lot. I've found that I've taken classes, and some of my classes have exams, and others don't have exams. Like some of these have to write papers, and I learn a lot from writing papers too. But when I have an exam, I have to know it cold going in, and that's hard to know it cold. But with practice, you can do it. You can certainly do it with practice.
If organic chemistry would go in down here, I don't care.
All right, can I clear this, y'all?
Yeah.
So for the second question, we did the 1.8 sine 37 and 1.8 cosine 37. Or is that going to be on the exam?
Yeah, you could potentially have to find the x and the y components. Yeah. So
Do you
that's.
have videos online?
Mm-hmm.
Oh, plus where you go for?
Sure. Yeah. So let's see. Hang on. Oh, that's the wrong thing. Sorry. So if you go back to Physics 101 into the screencast,
I remember chapter 4 had
yeah, so here are three, about 20 minutes or so about vectors on screen. If you just go to the physics search, physics, Phys 101, or just go to our course website and it says Phys 102 in the URL, just put a one, Phys 101 instead of Phys 102. Or you can send me an email and I'll send it to you. Okay? Or you can come to my office and we can sit down for 20 minutes and you'll be a pro at it. Okay? That was a hard test. Okay, we can do, can I do some other questions or you have particular questions?
I guess I kind of understand the difference, but I remember we would have these problems where you either have to use the electric force or the electric field one, and then you have to find the acceleration.
Oh, yeah. Mm-hmm.
Then I remember I kept doing the electric forces, but I realized it was the electric field.
Hmm. Well, like this one, a proton is 3 meters from a 1 nanocoulomb charge. What acceleration does it experience? Yeah. So the first thing, you know, we're looking for the acceleration. I know from Newton's second law, the acceleration is F over m. That's not on your equation sheet. You sort of need to know that. All right. And so I know the mass of a proton. This is on your equation sheet. It's 1. Yeah. Yeah, that's right. And so that's the mass of a proton. And I can find the force. It's going to be 9 times 10 to the 9th times the two charges, 1.6 times 10 to the minus 19. That is, you know, a proton. That is on your equation sheet. But you need to know, it's not listed as the charge of a proton. It just says 1e. It's the fundamental unit of charge, which is the charge of a proton and an electron. The next charge is the 1 nanocoulomb charge divided by the distance, 3 meters squared. And so I can cancel out some stuff here. That goes with that. This 9 goes with that. And my force is 1.6 times 10 to the minus 19 newtons. And then the acceleration is F over m. So you say 1.6 over 10 to the minus 19 divided by 1.67 times 10 to the minus 27. That's basically 1 times 10 to the 8th. So C is the right answer. I know that because these two things cancel out basically because they're about equal. And 10 to the minus 19 over 10 to the minus 27, I add 27 to negative 19. I'm bringing this up. But you can do it in your calculator too if you want. We had some, you might also see a kinematics problem like we did in class, where I ask you, what is the velocity after such and such time? If that's the case, you would find the acceleration, 1 times 10 to the 8th meters per second squared. And then if you want to know the velocity, it's going to be v equals v naught plus at. So you just multiply this times whatever the time is. And again, you're only going to have one problem maybe if you have that on the test.
Do we assume that V naught will always be a 0?
Yeah. Yeah, it'll say that in the question. I mean, it didn't have to say that here. So what was I saying? Oh, maybe have one question with where you'll need a kinematics equation, but I'm not going to give you the kinematics equations. There's only those two. There's that one, and then there's also the position equation, x equals v naught c plus 1/2 a t squared. I'll give you everything else, but not that. So F equals ma, and then those two kinematics equations. So Ryan, you might want to write those on a post-it note and put it on your bathroom mirror or something. Okay?
Can I ask you a really stupid question? I know you mentioned it several times. How do I find the E button on this thing?
The E button is very nice when you go to scientific notation.
Because I see the little E, and I know
It's right here.
that's
Either set. So like I want to do 1 e to the 10th.
Okay, so I always have double E.
Yeah, that's what I think. Double E. I don't know why they use 2 e's.
Yeah, because I see the, I kept using the little E and it didn't work.
I don't know if you have this on yours, but you just have the caret.
What about this way? E and
No, that's a natural. I'm sorry. Just whenever you do scientific notation, put them in parentheses.
Yeah, that's what I'm usually.
Yeah, I put it in parentheses and in brackets and everything. It takes forever to put it all in.
I know.
The letter E's in this one.
It would really help you, yeah. But fortunately, I try to make the numbers really easy. Like you're seeing on all these, that a lot of the numbers cancel out. And I try to make it as easy as
I
possible.
remember on that last test, I think I had to measure a cubic or something, and like I had to multiply so much that I kept getting the wrong answer.
On my test?
Yeah, like I don't know, it's like something about a tin.
Oh yeah, the Young's modulus.
And like I was
Right.
like, oh my gosh.
Okay. Can I take this away, y'all? Let's look at one other. Electric fields, that? You'll have one of those where I give you an electric field distribution and ask you a charge or something like that. On these, you, like for example here, Q2, I tell you is plus 2 coulombs. And so if I want to know the charge on Q1, I would count the field lines. Notice there are 4 field lines on Q2. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 field lines. That means that it's going to be 4 times the charge because I have 4 times the electric field lines. And so it's going to be also positive because the field lines are leaving. So it's going to be D. 4 times the charge of Q2. Sorry, not D. C, right. Because it's 4 times the charge. I have 4 times the field lines, 4 times the charge. You'll have one of those for sure.
Yeah, I think the one thing I have to watch out was for if it's positive or negative, because I have that.
Yeah. If they come out of the charge, that's a positive field line. If they go into the charge, it's a negative field line. And if you're ever uncertain, take out your positive test charge and put it right here and ask yourself, well, if the field lines are away, that means that this has to be positive because that would be the direction of the force, away from that positive charge. If this was negative, on the other hand, then the field lines would be going in that direction because a positive negative charge would be attracted.
And those ones are both positive.
Yeah, and this one they're both positive.
I have one quick question about this problem. Okay, for whatever reason I thought it was 16. Why is it 8?
I thought it was 16 too, right?
Yeah.
Because I counted up 16 field lines here,
And it's
and I thought, well, I was going to go with
I
16.
was thinking 4 times 4 is.
Right, so I have 4 times the number of field lines, So at 4 times the charge. This charge is 2, 4 times 2 is 8.
Oh,
I made the same mistake, didn't I?
so we were looking for the charge.
Right, I'm looking for the charge
Okay.
of Q1. Just have to be really careful. Read it very
Yeah, because there was a different problem where, I don't know if it was asking for the charge, but it would have been 16, I think. If I remember.
Yeah,
I don't know what it was
I
asking.
use a problem to not make that mistake.
Right.
Yeah. I just organize things and really.
Let's look at 15, because that's kind of a cool problem. I haven't made out the test, so I'm not saying this is on the test. I haven't made out the test yet, but it is a good problem. A charge of plus 2 coulombs is at the origin. When a charge Q is placed 2 meters along the positive x-axis, the electric field at 2 meters along the negative x-axis becomes 0. What is the value of Q? So what we're saying here is that the electric field at this point x is 0. Now the electric field due to this charge is going to be in that direction. And so now what we're saying is that the electric field due to this charge is in that direction. So I know one thing about that charge is that this charge is negative, because if I were to put a positive test charge right here, it would feel an attractive force to this charge in order to give me an electric field in this direction. Let me restate that. So the plus 2 Coulomb charge puts an electric field to the left, because my positive test charge would feel a repulsive force, so I draw in that direction. So if the electric field is 0, I have to have a vector that's equal and opposite to this vector to give me an electric field of 0. So this vector has to be in this direction. That means this charge has to be negative. I mean, they're all negative anyway, so I'm already stating this doesn't really help me that much. So now I want to think about, well, what is the electric field? So I've doubled the distance. So how must the charge be different? Must the charge be bigger or smaller than the 2? It has to be bigger because it's farther away. It's twice as far away, so we'll write that equation for E. There's a hard way to do this, but this is the easier way to do it. KQ over R squared. I've doubled the distance. So what, in order to get the same magnitude electric field, what must I do to Q? I have to have a factor of what in the numerator? I have to have a 4 in the numerator. And since this was 2 coulombs, that second charge has to be 8 coulombs, or negative 8 coulombs.
This is my problem. Why don't we use Q? Because then I keep thinking about like force and opposite. Like I have a trouble determining between if I use like the electric field or the electric force for the coulombs.
Okay, well, it says electric field. So it's an electric field. It'll always say, just read it. It'll always say whether it's the force or the field.
Okay.
It shall always say that. Okay. You know that one? That's a good question.
Yeah.
I think I might put that one on the test. We'll see. I don't know.
Put it so then I will know what to do.
Right. And there are 4 questions on the test from the concept code. So I don't know if y'all are reading that. You don't have to do it. That's okay.
I couldn't find the answers in all of them. In the explanation, like in the first part you read, I couldn't find all the answers. Like when I went to do the actual.
Oh, really? Like in the text?
Yeah, I couldn't find them in the code.
Okay, we always keep doing it.
Some of them I got more wrong than I got right.
Okay.
On them, but I didn't.
Just keep doing it if you wish. I mean, you don't have to do it to know the answers to the questions. We'll cover that material in class, but that way you'll see questions that are familiar to you.
But I
And there are,
want to do well in the class because
I want you to do well too.
more questions. So if I don't know, then that's so bad.
Right. Okay.
I have a super general question.
Okay.
No, this course, Physics 2 compared to 1, is it like way harder or?
Some people say that these first 2 chapters are the hardest of all semester.
Okay. But does like, in general, is it harder than Physics 1 was?
I think that
I thought the end was
it
very
depends. I mean,
challenging.
y'all did pretty well in Physics 1, so.
I just didn't, I think I got this in general.
Yeah, we're not gonna see that again.
Never got that.
Oh no, we will see it again.
It's on the border a lot, but.
I remember.
I cried.
Yeah. So don't know. Some people it's
It's a
easier.
wash, it's about the same.
Yeah, once we get into circuits, the circuits are different from anything we've ever done. But some people are really good at circuits. You sort of have to be able to see things spatially, and so some people are really good at that.
See, I like the charge stuff. I find this.
This is a lot like what we did last semester.
Yeah.
That's why I
Vectors.
like it.
Right. We're gonna move away from this soon. The average is usually a little higher in the second semester, but the students are better in the second semester.
That's fair.
There's fewer go. Just because people don't have to move on or what various reasons. Students are good. They are good students in this class. They're like the best at the university.
I'm surprised that I'm doing good because I never had a business class in high school.
All right. Any other questions? I'm inclined to wrap it up today if that's okay. Okay, let me pause.
There'll be a review next week.
Of course.